Hello, my name is Jianxin, CST2509054. Let me introduce task 1 for you. First, we create a struct and type define it as not. It has value and 2 pointer, previous and next. And then display forward, we need a copy of head. And here is a while loop. We use if the temp doesn't equal to now, which means the temp isn't out of range, so we print out the value and use it to go through the linked list and print every value. Very easy. And then it's empty because we initialize the head pointer and the tail pointer as now in the main function. So if it equals to now, so it is an empty linked list. So we return it as true. Else we will return false. Very easy. And insert at beginning, we need head, tail, and value. We allocate a portion of memory in the size of a node, and create the new node to point to let it point to the portion of memory. If the new node equals to now, which means the memory allocation is failed, and we return. Else, we just let the new node's value equals to value, and because we insert at the beginning, so the new node must be the first node, so the new node's previous must be now, and new node's next must be the originally head node. And if the head equals to now, which means before inserting it is an empty linked list, so the head and tail both points to the new node. Else the originally head node's previous is the new node, and let the head pointer points to the new node. Very easy. And then comes to the delete at beginning. We let temp equals to head, and if head after checking whether it is empty list, we just let the head pointer points to the second node, and if the second node doesn't equal to now, which means because the second node now becomes the first, so its previous equals to points to now. Else, which means after deleting, it becomes an empty list, so the tail and head all becomes now. It's an empty edge situation. And then after that, we print the message and free the memory, and comes the delete at position. We need head, tail, and the position, which is the index. And after checking whether it is empty, we if the position equals to 1, we can use the function we just mentioned, and we use the temp to find the node previous to the node which need to be deleted, and we use this to go through and find the target, and it is an edge situation. If the temp equals to now or temp's next equals to now, which means the target is out of range, so we just break. And it is out of range, so we use this to skip the node which needs to be deleted. Very easy. And the temp is just the node needs to be deleted behind. Is the nodes previous to the node need to be deleted, which needs to be deleted. Yes. And if the node after the target exists, so the node's previous must points to the temp. If it doesn't exist, so which means the target node is the tail. So after deleting, the tail must point to the temp. Yeah. After that, we free the portion of memory to delete node. Yeah, very easy. And find node, we need to offer the value and the index. Index equals to 1, and then we go through the linked list. If the temp's value equals to value, and we just return the index. Every time go into the loop, the index will increase automatically. If we doesn't find the target, we just return -1, which is a symbol of failure. And the delete node, we need the value, and we need to find the index, so we call the use list function first. And if it is -1, it failed, so we just print out not found. Else we call this function to delete the node, the target node. Very easy. And this destroy list at the last of the program, we must use this to free the memory, to release the memory, to avoid memory leak. So while loop, while we use this to go through the linked list, we create next to equals to the temps next to avoid losing the linked list, and we free temp and let temp equals to next, and then go through the whole linked list and free every node. After freeing, the head pointer and tail pointer also points to now, to avoid becoming wild pointer. Yeah. Also edge. No. Yeah. And then come the main function. We initialize head and tail as now, and we declare this variable out of the switch case to avoid some syntax error. Here is the menu display, and we use switch case. And let's try it together. We insert 219. Okay, every time we execute it, we will also get the content of the linked list. So it's very clear. And we use case 2. We need to find a node. We insert a value. Okay, we got the index. It's the third node because we use insert at beginning, so it will be the third node. And then delete node. Okay, I want to delete it. Okay, it is deleted successfully. So the false display. Okay, very clear. And check if it is empty. It's not empty. Okay, now we deleted all the node. Okay, let's check where it is empty. Yeah, it is empty now. Okay, and then case 6 exists. Okay, case 6. Okay, it exists, and we destroy and free all the memory. Okay, very easy. It is all for that's all for my part. I display and complain and explain all the function I create and the edge situation. Thank you very much.
So hello everyone, my name is Wang Haokun and my student ID is CST2509043. So today I will present our work on task 2, implementing a stack using a similar linked list. I will just show our core concepts, the logic behind our functions, and the program's overflow. So, and finally, I will just show what I learned from this assignment. So let's start with our structure. So why we choose a linked list rather than a simply array. So the firstly, its advantage is that it can dynamic memory allocation. So an array requires fixed size, which lead to waste memory and a strict limit on how much data we can store. But by using a linked list, our stack can grow and shrink according our true needs. So completely avoiding the standard overflow or the uh, waste of memory. So to control the structure, we use a single global pointer called top. So we can also see that in our code. Okay, so that because a stack strictly follows the LIFO principle, so the top pointer acts as the location that where is the head of our stack. So it can help us to entry and exit point of our data. So then let's move to our core operations, push and pop. And we use the add function and withdraw function to represent it. So as for our add function, the logic is straightforward and efficient. So firstly, when a user inputs a value, we first use malloc to allocate memory for a new node. So if the memory is successfully allocated, we come to our three steps. So firstly, we store the user's data into the new node. Secondly, we point this new node's next address to the current top of the stack. Finally, we update the top pointer to become the newly added node. So it is exactly like placing a new plate on top of a stack plates. So next is our pop operation. So firstly, before we remove our node, we must perform a crucial safety check for the stack underflow. So if the top pointer is null, it means that the stack is totally empty. So in this case, we print a clear error message and return -1 to prevent the program from crashing. And then if the stack is not empty, we simply remove the top item or create a pointer to hold the current top, and then move to the global top pointer to the next node. So crucially, we then use the free function on that temporary pointer. Releasing this memory is essential to prevent memory leaks. And then it's about the display function and the counting function. Okay, so the key concept in this function is safe traversal. So we must never move the global pointer to read the list. Otherwise, we would destroy the entire stack because we cannot find the address of each node. So that we use a while loop to move this current pointer down to the list until it is null in the current node. So for the display function, we present we so for the display function, it just print the data during the top to bottom traversal naturally, output the elements in reverse chronological order. So it just demonstrates the LFIFO structure, and for the counting function, we just increment a variable during the loop to track the total number of our nodes, and then we come to our free stack, so that when the user chooses to exit, the function loops through the entire remaining list and free every node one by one by use the to pointer so that it ensures our program to terminate cleanly with that without any memory leaks. Okay, so let's come to our program flow. So we use a switch case statement inside a while loop, and it also cooperated with our like the uh, robust check. So it can help our users to input valid value. Okay, so if a user accidentally types a character like the key like A, and when scanf is read this, but it find that it's not the integer, so it will just to give a prompt that invalid input. And also, if he just input a number but is out of the range of 1 to 4, it will also give you the prompt that is an error. So we can see from the run our program, if we choose the number A, it's the invalid input. If we choose the 5, yeah, we also can give you the prompt. So that's our robust check. And also, if we just choose the 1 and we enter the character, so this is the mainly through robust check in our program. So then I will just give you an example of how it can successfully execution. So we can see from our program that if we just input 556, 445, and then we remove the 1, we can find that it just very perfectly uh, meet our requirement. The last in is 445, and the first out is also the 445. So it's just like a stack. So to conclude, this assignment was highly rewarding. It just deepened my understanding of how the pointers work and how we just handle when we just meet the unpredictable user input in the menu. And so by researching and implementing the buffer cleaning techniques like the getchar, so I learned the importance of the defensive programming. So we must not only write code that works under perfect condition, but also to deal with their invalid input and give them the proper prompt. So this is the end of my presentation. So thank you everyone. So